Okay, here we go. So last time we were talking about. Sorry, let me get this out of the way here. Okay, last time we were talking about equations in polar coordinates, and we'd made it through these two examples. Again, keep in mind the big idea is that if you're clever about how you manipulate the algebra around, you can turn equations that you're given into equations where you can make easy substitutions, like I did here, right? It's just nice and handy, and then the punchline is familiar rectangular equations that you already know how to do stuff with. Okay, fine. So let's move on from there. The next example, this is a little bit clunky and heavy-handed and a lot less satisfying than that last example, or the last two examples. But sometimes you're stuck, and sometimes you just have to do this. And the thing is, if you try to manipulate this equation around, to turn it into something where you can just plug in, oh yeah, x squared plus y squared, and stuff like that, you're going to fail. It just doesn't work. It's just no good. Right? So what we have to do sometimes is just brute force plot points. And so here we go. I'm going to kind of plot a bunch of points at the same time. I'm going to do in parallel point plotting. I'm going to start off by thinking about what happens as I rotate through the first quadrant, which of course means theta is going to go from 0 to pi over 2. Right? And okay, so what happens is as theta goes from 0 to pi over 2, well, here it is. There's theta. Notice, very importantly, theta is not what we're plugging into the sine function. We are plugging in 2 theta. That's what goes into the sine function. 2 theta doesn't go from 0 to pi over 2. It goes from 0 to pi. Right? So the thing that I'm plugging into the sine function goes from 0 to pi, during which, let's see here, r, namely the value of sine of that argument, is going to do, as I have drawn here, the values start at 0 and then go up to 1 and then come back down to 0. That's just how the sine function works. Okay, is everybody with me so far? Okay, now how do I put this information onto the xy plane, interpreting these things as polar coordinates? Well, you got to keep in mind what these things are. Theta represents a direction, for example, coming out of the origin. And so you've got to imagine, as we start to plot these points, that theta is going to start like that, and then it's going to where our direction is going to kind of keep changing, rotating around toward pi over 2. And in those directions, what I'm going to be doing is I'm going to be moving outward from the origin as indicated by these values of r. So as my direction turns, I'm going to be moving outward first by 0, then by small amounts, then increasingly, and then up to all the way out to 1, and then decreasing, and then all the way down to 0. So putting all that together, theta is small, r is increasing, theta is increasing, right? Eventually up to it reaches a maximum there when we're sort of halfway through. And then from there it starts to decrease as theta continues to increase until it gets back down to 0 when we're done. And so in some sense then this curve, if you will, that curve, an arc of the sine wave representing r in polar coordinates ends up looking like that in the xy plane. Everybody see that? It's geometrically a little brain bendy, right? That's what happens. All right, let's take the next range of values. Let's see. We just addressed what happens as theta goes, if you will, through the first quadrant. So now let's move on and think about what happens as theta moves along the second quadrant. In other words, from pi over 2 to pi. Well, again, be very careful with this. That's what theta is doing. Theta is not what goes into the sine function. It's 2 theta that is the argument of sine function. So 2 theta the part that the inputs to the sine function go from pi to 2 pi, during which sine looks like that, right? And so in particular then, the values of r start at 0 and go all the way down to -1, and then start to come back up and make their way back up to 0. And now again, we have to kind of think it through. Okay, what does that look like as my theta is doing this? As my theta starts from straight up and moves counterclockwise to horizontal, how do I represent r being these values? Well, very importantly, these values have r being negative. And keep in mind, negative means you go backwards, not forwards. Right? So this is a little bit weird to think about, but so for example, a value of theta kind of like that, a negative r value puts you back here. Everybody on board? So, all together then, we're going to get things that look kind of like this. And said differently, this kind of arc of the sine function there in rectangular coordinate, representing polar coordinates in the xy rectangular plane, looks like that. Yes?
So that's the xy plane, but you described it as a radius, just for the sake of argument, from converting from a polar thought to a...
So what I was plotting here was r as a function of 2 theta, right? Because 2 theta is going from pi to 2 pi. Does that make sense?
Yeah. Okay.
Yeah. So this is... I didn't label the axes because I didn't want it to get weird. Right, but just in terms of what goes into the sine function, what comes out of the sine function, this is what's happening. Yeah, that's right. Okay. All right, now what I'm going to leave for y'all to think through is, in some sense, the rest of it. So we did, if you will, the first 2 ranges of values. We talked about 0 to pi over 2, pi over 2 to pi. And now I want y'all to think through the rest of it, and what you're going to find as your answer, just so you know, is that this pattern of kind of moving around like this continues. And you get a little 4-leaf clover. Is that cool? Everybody's happy? So again, think it through. Make sure you're comfortable and that you get these other things that I claim you get. All right. Okay. Sometimes you can be trickier with the algebra. Now we see a situation here where we have an r on the left. We were very happy last time we saw this where let's square both sides of the equation. That gives us an r squared. We love r squared because I can write it in rectangular in a snap. It's super convenient. Excuse me. Excuse me again. Not so in this case. If you square both sides, what happens to the right? You get cosine squared. Cosine squared is not... Oh, my God, the chalk is getting to me. Sorry. The cosine squared is not a... Oh, man. Oh, my gosh. I'm sorry. I hope I got rid of that now. Okay. Cosine squared is not something convenient in rectangular coordinates. So, no luck. Oh, man. So, the nice move here is to multiply both sides by r. You know what? I'm going to get a sip of water. I'm sorry, y'all. I'll be right back. Just take a second. Okay, fingers crossed. Okay, so what we do, instead of squaring both sides, we multiply both sides by r. And that has the nice effect that we still get the r squared on the one side, but then instead of having some weirdo like cosine squared, we get r cosine theta, which is also something that we recognize, right? So lucky break, and there's a different trick for every circumstance, and you can't memorize like a list of cases of always do this in the following cases or whatever. It's just, but there's a different trick to keep in mind that sometimes is helpful. Okay. All right. Now, I'm also going to point out this opportunity that turning this into an equation that we recognize is a flashback to high school algebra. This is called completing the square. I think a lot of students are too much time has passed and maybe don't remember how to complete the square. I was told incorrectly when I was in high school or whenever that was that if you know the quadratic equation, you don't need to know how to complete the square. That was horrible misinformation. It's just not true. And here's a great example, right? I'm not solving for x. So the quadratic equation doesn't help me, right? So anyway, make sure you're good with completing the square. I'm sure there's plenty of internet resources for that if you're maybe forgot how that works or whatever. If you can't find an internet resource that you like, come to my office hours. I'll be very happy to show you how to do completing the square and talk about tips and tricks and stuff like that. Okay. All righty. So moving along. Going the other direction, going from a rectangular equation to a polar equation tends to be easier. It's pretty much just a matter of plugging in the known formulas for x and y. That's kind of all there is to it. No big deal. There are a couple of shortcuts. You'll notice here I kind of multiplied out that one term first. The reason I did that is because then I get kind of lucky here. See, it's not just me. Yeah. You get kind of lucky here that now I don't have to plug in a trig formula for x and y, right? I have a convenient existing relationship, x squared plus y squared, r squared. Boom, no problem. Okay, so that just saves you a little bit of effort there. Okay, all right. All right. Okay, so moving to cylindrical coordinates. I'm going to be quick with this one because there's really not that much to say about it. A lot of people call cylindrical coordinates polar coordinates in space or polar coordinates in R3. And that's fine, I guess. I also, though, think it's a nice way to think about it because, after all, look what we've got here. We are literally, as far as x and y are concerned, we are using the exact same relationships. We're drawing the exact same picture. Theta measured counterclockwise from the positive part of the x-axis, all that business. The only thing that's different between polar coordinates and cylindrical coordinates that we're seeing here is that there are 3 coordinates to begin with, and we just kind of keep the z. So the third rectangular coordinate is z. The third cylindrical coordinate is also z. So, it's again pretty reasonable to think about this as being polar coordinates in space. But that's more syllables than cylindrical coordinates. So I'd rather just say cylindrical coordinates if I could talk. Okay. A couple of quickie observations. If you have r equal to a constant, that makes a cylinder, which is why we call this cylindrical coordinates, right? R being distance from the z-axis, right? Okay, let's see here. A sphere, here's the equation of a sphere in rectangular coordinates. Easily converted, because there's that easy relationship, sort of a cylindrical to rectangular conversion. X squared plus y squared is r squared, thus resulting in an easy cylindrical equation for the same sphere. All right, done. couple of freebies. Here's a harder one. There's a really nice trick in this next example. And here we go. Z equals KR. I claim this is the equation of a cone. Harder to see right off the bat. But here's the nice observation. One of the big takeaways of this example, notice in this equation, no thetas. And y'all may recall, we saw a situation kind of like this once. We saw equations of planes where there were no y's. And it turns out that plane's parallel to the y-axis. Here's another way to say that. When there's no y's, any value of y that you pick, any plane that you look at that represents a constant value of y, any plane perpendicular to the y-axis, those cross-sections all look the same. Of course they do. They only differ from each other by different values of y that isn't even in the equation. The equation doesn't change a bit when you change y. So likewise here, the equation doesn't change a bit when you change theta. Let theta be whatever value you want. It's the exact same equation. And so again, we get the exact same cross sections, right? So in this, what you might call theta slice, representing a value of theta, well, you're going to have some cross section. And likewise, if you were to take a different value of theta, different theta slice, as it were, whatever, you're going to get the exact same cross section because it doesn't show up in the equation at all. Okay. So all of these cross sections are actually pretty easy to describe because, well, it's just z is a multiple of r, and so all of these cross sections are basically going to be straight lines like this. And so you just imagine then a bunch of straight lines like this in each one of these planes, and now we have a sort of an art problem of how to draw this. Anyway, that was a mistake to try. But let's see. Let me do it one little bit at a time. Let's start with the positive, right? The positive values of r there, and we're going to get cross sections that look like that for every different value of theta. Okay. This gives us the sort of the top part of the cone, and then you can also imagine, well, what happens down here when r is negative and z is negative? Which is, by the way, perfectly fine. There's nothing wrong with r being negative. Right? And for those negative values of r, you get this business down here, sort of the bottom half, if you will, of the cone. Everybody okay with that? Nice general rule of thumb. If you have a cylindrical equation that has no thetas in it, that's rotationally symmetric around the z-axis. It's pretty awesome. Nice one of these, casual observation leads to powerful geometric conclusion kind of examples. Okay, real quick, be careful using r as a radius from here out. R is now spoken for. Dibs has been called. R is a variable. Kind of like X is a variable, right? I mean, you wouldn't go around, like if you were drawing a triangle, in the XYZ space or even just in the XY plane, you wouldn't pick some random arbitrary distance and call it X, right? You can't. X is it's a coordinate. We're doing things already with X. You can't just use it for something else. Likewise, R no longer can really be used because it's now a variable. It's a coordinate variable for a coordinate system. Okay. All right. Okay. Moving to spherical coordinates. This one's tricky. Geometrically challenging. You're going to have to do some three-dimensional thinking here. This is unavoidable. This is intrinsic to what it is. There is no algebraic workaround. There is algebra in it, but there's no way to get rid of the geometry. So you have to sort of, plan to think three-dimensionally. And by the way, also plan to get good at making three-dimensional drawings. Also really important. We'll talk more about that as time goes on. Actually, you know what? While I'm here, why don't I just go ahead and give the giveaway on my YouTube channel here? Various different little short recordings on various different topics, and I'm going to point specifically to these two right here, drawing 1 and drawing 2. This is everything that I know about how to draw three-dimensionally in a multivariable calculus class. That's exactly what these videos are made for. So if you're not that good at drawing three-dimensionally, well, you're going to have to get good at it, and this, I hope, will be helpful. And there may be other resources online that you might find more useful. I don't know. Okay, so let's talk about spherical coordinates now. Again, geometry is going to be part of this. Here we go. Theta is our first spherical coordinate. It is the exact same theta that we've seen before. It measures how far, if you will, rotating counterclockwise from the positive part of the x-axis. I like to think of theta as defining a half plane, which extends infinitely upward and infinitely that way and infinitely downward. But it does not extend infinitely the other direction. It's been cut on the z-axis. The z-axis is effectively the hinge on which this, if you will, kind of door is swinging. Okay. So I like to call it a half plane hinged on the z-axis. Okay. Okay, so that said, let's see here. Let's talk now about, I was going to leave this though. Okay, so what is phi? Phi, another Greek letter. You're going to see various Greek letters in this course. Phi defines an angle measured off of the positive part of the z-axis toward the theta half plane. So very importantly, not just in any sort of random direction, right? No. It is defined as an angle measured into that theta half plane specifically. Is that cool? That's for, I should say, for positive values. If you have a negative value of phi, well, as you might expect, you just rotate the opposite direction, exactly away from the theta half plane. All right, so that's what phi is. And then, now, what is rho? I'm going to first observe that once you know theta and phi, I should clean up this thing. Once you have theta and phi, between the two of them, they define a direction out of the origin. Right? I mean, given a theta and a phi, that defines, there's only one direction out of the origin that would have that theta and that phi. And given that direction, rho, Greek letter rho, lowercase Greek letter rho, it's kind of like r in polar coordinates in the sense that it's, I'm going to again commit the math crime and say how far as if it's a distance, and it's not. We'll come back and tweak that in a second. It says how far, if you will, to go in that direction, and altogether then that defines this point that has those spherical coordinates. Okay, how are we doing? Yeah.
Is theta always coming out of the x-axis?
Yeah, theta equals 0 is defined as being in the positive direction of the x-axis. That's right. Yeah, and then it's measured from that. Yeah. Anybody else? Yep.
What is R?
What is R? Let's see here. So you're talking about this R right there? Yeah. So I haven't had any use for that just yet, but that's the usual cylindrical coordinate R. And we're going to make a reference to that in a couple of seconds here. But for the moment, we haven't really done anything with it yet. Yeah.
So sorry, is rho like the vector going out in that plane?
Well, rho is a coordinate. It's not a vector, right? So rho says how far to go in the direction that's defined by theta and phi, right? But it's just a coordinate. It's not a vector. Yeah, and then in the back, yeah.
Since theta defines a half plane, can it only be positive?
I hear where you're coming from. I'm going to say it defines a half plane, right? But theta can kind of be any direction you want, right? And it defines a half plane, but then phi, let's say theta defines this half plane, right? Positive values of phi go that way toward the half plane, but negative values of phi go back the other way, right? And so notice I didn't say that the point has to be in the half plane. It's just that theta defines a half plane. Does that make sense?
Yeah.
Okay. Yes.
But could you just use the cylindrical ones for this or no?
Do what now?
Could you just use the cylindrical coordinates for this or no?
Well, I mean, yeah, that's always an option, right? I mean, cylindrical coordinates is one way to describe a point. Rectangular coordinates is another way. What I'm doing here is describing how to use spherical coordinates. Yeah, and I mean, in some sense, all coordinate systems are always an option, but some are going to be better than others in certain circumstances. Yeah. Okay. All right. Okay. Now again, I have to fix my little math crime here. I as usual, said that rho was how far, as if it were a distance. It's not. It's a coordinate. It's perfectly allowed to be negative. So what do you do if rho is negative? And, well, if rho is negative, you just go backwards, exactly as you would sort of expect. So negative rho would just have you going the exact opposite of the direction that phi and theta define. Okay. All right. Now, let me clean up the mess and talk about conversion formulas. Let's see here. Okay, so I'm going to focus now on this right triangle that I have in yellow there. Tragically, we're looking at it at some kind of a weird angle, and that can make things confusing. So just to help us out, I'm going to redraw it. This is the exact same triangle, but just we're looking straight at it, so a little bit more square, if you will. Notice that this side of the triangle is R. That's our cylindrical coordinate R, somebody asked a minute ago. And then notice that this side of the triangle is, well, it's height, right? That's the Z coordinate of that point, and Z, therefore, is what this is. Notice further that, let's see here, I'll do it like this. Rho, being that coordinate, is the hypotenuse. And phi, being that angle, is also that angle. Everybody with me so far? And we're actually in business now. We just have to write down some really simple trig. The trig of this triangle, I think, makes it pretty easy to see that R is rho sine phi, and Z is rho cosine phi. Real easy trig. Right? Everybody remembers their trig. And we're actually done, believe it or not. Just making these two innocent little trig observations about this triangle. That R is rho sine phi, Z is rho cosine phi, and we already have our spherical conversion formulas. Because after all, X and Y, we already knew. X and Y are R cosine theta and R sine theta, and we just computed R in spherical coordinates. And let's see, so we have X and Y, but now we also need Z. Okay, well, yeah, but the Z formula is literally something we just wrote down, right? So wonderfully convenient. I advise that you not memorize these formulas, or at least you don't have to, but you will need to use these formulas, and they won't be provided. What I'm suggesting is not that you try to memorize them, but rather that you just understand how the real simple trig of this little diagram will derive them for you in a snap, right? And for whatever it's worth, I mean, everybody's different. Maybe you're better at memorizing than I am. I'm really bad at memorizing things. Anything rote, oh man, it's hard for me. I'm just no good at it. And I don't trust myself. Right? I might have something correctly memorized, but I don't believe that I memorized it right, and so, my gosh, I just don't trust it. But I understand the picture, and as needed, I can rederive anytime. And I've re-derived these formulas with exactly this trig probably thousands of times in my life, right? Again, second major in physics, you do a lot of spherical coordinates in physics. It's extremely useful in physics. And every time I needed them, that triangle right there. All right, is that cool? Now, if you would like, in addition, also to memorize them, just for quickness purposes, sure, go ahead. I think that's reasonable. Okay. All right. Okay, let's see here. Moving along. There we go. Okay. A couple of freebies. Pretty straightforward to see. Rho equals constant is always a sphere. If you think about it, again, rho just literally means distance to the origin. Okay, distance, air quotes. As long as C is positive, this rho is then a distance to the origin, and if distance is a constant, then that's obviously a sphere. Okay. Alrighty. Here's a hard one. You may recall in polar coordinates, there were kind of two different ways to represent a point in polar coordinates. Right? You can you can have the theta pointing toward the point, in which case r is positive, or you could have r being exactly away from the point, in which case you just, that being your positive r direction, then you just have r be negative, and it gets you to the exact same point. Okay. Well, there's two different angles in spherical coordinates. So in the same way that there are two different possible values of theta, and we're going to talk through these details in just a minute. For each of these choices of theta, there are two different possible values of phi. And so grand total, there's going to be 4 different ways to write a point in spherical coordinates. And the geometry gets confusing. So it's good to spend some time practicing this, thinking about it. Along those lines, I'm going to show you 2 of the different points of view here. And I'm going to leave the other 2 as a practice exercise. And of course, you're very welcome to come to my office hours if you want to, help thinking through it. If you want me to check your answers or whatever, just come on by office hours. Happy to help. Okay, so here we go. Talking about this point right here. It was observed in one of my earlier lectures today that I'm breaking my own rule here. I didn't tell y'all which coordinate system this is using, right? So, my bad. Sorry about that. I mean rectangular coordinates here. So, x is 1, y is square root of 3, z is 2. Okay. All right, so that represents this point right here. And trig, again, flashbacks to high school. You can persuade yourself of these various different distances that I have labeled in here and these angles like that. So, anyway. Make sure to think through the trig and all the Pythagorean stuff, and make sure you're clear on all the numbers in this picture. Okay. Now that said, let's talk theta. I'm going to start off. Well, I'm going to discuss the theta equals pi over 3 option. After all, that's what this angle is. That defines this half plane. Notice that my point is in that half plane. Cool, right? As desired. And now here's your options. I claim there's 2 different values of phi. That'll get you to this same point. The first one is the obvious one. Keeping in mind, phi is measured off the positive part of the z-axis. Phi goes into the theta plane. There's our theta half plane. So this value of phi right here is just pi over 4. Nothing to it. Everybody okay with that so far? So theta equals pi over 3, phi equals pi over 4 defines this direction, and once you have a direction, then there's just a question of what is rho, and in this case, we're going toward the direction that we've defined is going toward the point we want to get to, and so rho is just going to be the positive value of whatever that length is. That makes sense to everybody? Okay. Now, Let's talk about the other option, the weird option. Okay, the weird option is to observe that let's see here, I could view this point as being exactly opposite of that direction. Right, just going exactly away from where this point is. And I would get to that if instead of going positive pi over 4, if I went negative with phi by the amount that would point me exactly in this opposite direction. And if you think about it, this being pi over 4 means that the amount that I have to go in the other direction is 3 pi over 4. But keep in mind, because I'm going in the wrong direction, I'm going away from the theta half plane, this value of phi here is negative 3 pi over 4. Does that make sense to everybody? So let me write this down. So what I have in orange here is theta equals pi over 3. Phi equals negative 3 pi over 4. And that gets me going in, well, again, not the right direction. This gets me going in exactly the wrong direction, which means in order to get to the point that I want to go to, I actually need now a negative value of rho. So then let's see here. This would be rho, a negative value, negative 2 root 2. Everybody buy it? A little challenging geometrically, right? A little brain bendy, but this is how spherical coordinates works. Okay, so again, exercise for y'all to think through on your own. How would all of this change if you change the very starting premise? If we got rid of, the very first thing that I did here was talk about theta being pi over 3. What if instead we had theta being 4 pi over 3? Not, if you will, the sort of right value of theta, the obvious value of theta, but what if I went around back there? Right? We're going in the wrong direction. Right? So there's my theta half plane. This then is how phi would measure. Positive phis would go this way. And so notice one thing you could do is have negative value of phi. That would get you going the right direction. Or you could have a positive value of phi going all the way down to this way. That would give you going in the wrong direction. And then again have a negative value of rho, just to kind of hit the broad strokes there. So anyway, work out those details. I think it's a healthy exercise. And again, come to office hours if you have any questions. Compare with a friend, whatever. But office hours, we're very happy to walk you through the rest of the details. Okay. All right. Is everybody happy? Okay. All right. Here's a cool little application. Y'all know about longitude and latitude, I hope. If not, if you arrange the Earth with its center at the origin, north pole on the z-axis, positive part of the z-axis, and prime meridian intersecting the positive part of the x-axis. So set up in what I'm going to call the most convenient possible way. With that said, east longitude is measured like this. It's literally the spherical angle theta. How nice, right? Then there's this other map coordinate called north latitude, which is measured like that. And it's not phi, but it's closely related to phi. If you think about it, phi is that angle, and so not hard to persuade yourself that these two angles here, they always add up to exactly pi over 2, right? They you see it from the picture, they just clearly add up to pi over 2. And because they add up to pi over 2, there's an easy relationship between north latitude and phi. Is everybody happy with the geometry there? So pretty cool. Map coordinates very closely, not exactly, but very closely tell you spherical coordinates by this little easy conversion. All right, so who cares? Sorry, one little detail I left out. Rho, distance from the origin. Distance from the center of the Earth. Well, if you're on the surface of the Earth, then that distance is the radius of the Earth, which, by the way, is approximately that value. Okay, all right, so spherical coordinates. Here's a use of this convenient connection, and that is, let's suppose that you were in Oslo, Norway, and you were going to be flying to Durham, North Carolina, let's just say, right? And you want to compute what is this shortest possible path, right? How far is that? What's the distance? And if you look at a map, if you look at a Mercator projection, you're going to be tempted to think, well, I guess I'll just draw a straight line there or something, and I guess that straight line is the shortest distance. It's not. Mercator projections are all messed up, right? In fact, all projections of a round, curved thing into a flat piece of paper, they're all bad in their different ways, right? But anyway, the point is, it's just not a triangle. And if you think about it, I mean, you can see right here why it isn't. After all, this is what you might call the longitude part of that would-be triangle, and this is the sort of latitude part of that would-be triangle, and just very clearly not a triangle. These are a bunch of curved lines, not a triangle. There is no Pythagorean rule there. You got nothing, right? Okay. All right. So how do we compute that distance? Big deal for airlines, by the way, right? Got to know these distances. Okay, well, here's the beautiful idea. If you know longitude and latitude, which are well known, right, easily Googleable, right? Well, as we just discussed, you can use longitude and latitude to compute spherical coordinates, and as we discussed on the previous page, you can use those to compute rectangular coordinates. And if you know the rectangular coordinates for Oslo and Durham, well, it's really easy to write down the dot product. Dot products are really easy to compute in rectangular coordinates. Now, I emphasize only in rectangular coordinates, right? This dot product formula, the whole, x1, x2 plus y1, y2, or, however that goes, right? That only works if those coordinates are rectangular coordinates. Cool. Well, that means that if I can compute the dot product, then I can compute magnitude of x1 times magnitude of x2 times the cosine of the angle between them, because that's what dot products are. And notice that the angle between them, what I'm calling alpha here, that angle between them, easily solved for in that equation. That is what you multiply by radius to then get the distance that you're actually interested in. That distance, radius times alpha. Handy little process, right? Now there's a lot of details in there, right? There's going to be a lot of arithmetic in cranking out what the x and y coordinates are. You're going to need a calculator to compute sine of this and cosine of that. But bunch of arithmetic, but the punchline, I mean, this is a pretty straightforward little algorithm, and it computes this curved distance along the surface of the Earth without that much trouble. Everybody happy? All right. Converting from one coordinate system to another, it's very similar to stuff we've talked about before. It's really just a matter of plugging stuff in. For example, you'll notice here I plug in the established formula for x, and you just plug it in. And the punchline then is the rectangular equation gets turned into the spherical equation. Works out very nicely in carefully selected cases. There are plenty of cases where it gets really hard, but I'm not going to be giving you any of those bad cases. And, of course, notice I didn't plug these formulas in immediately. I went ahead and simplified. I expanded out and found all of my terms first, and that gives me this kind of convenient opportunity to save myself a bunch of trig just by recognizing that, well, x squared plus y squared plus z squared is already known. Okay. All right. Is everybody happy with that? Okay. So it's just like in cylindrical coordinates and polar coordinates, just a little bit different details. All right. Okay. So, last thing we're going to talk about real quick is standard basis vectors. We're not going to do very much with this. In fact, I don't have any particular plans to do anything with standard basis vectors in non-rectangular coordinate systems in Math219. That said, they may come up in other circumstances. They are very natural things, and they are something that you might need to be familiar with. Let me just talk very quickly about what they are. Of course, in rectangular coordinates, these are our standard basis vectors, which you know by various different names. Right? And they have various nice properties. One of them in particular, these vectors are unit vectors that point in the direction where exactly one coordinate is increasing and the others are, momentarily at least, constant. Right? So if I move in the direction of E1, then x would be increasing, but y and z wouldn't be changing at all. Okay. All right, so we can ask that same question in, let's say, polar coordinates. Right? If I'm at this point right there, which direction would I move to have r increase but have theta stay constant? Well, I'd go that way. And not hard to persuade yourself that that's the unit vector that points in that direction. Good little exercise, something to think about. What direction from this point would I go to have theta increase but have r be, at least momentarily, constant? Well, I would go that way. Now, if I go that way for a significant time, obviously r does get bigger. But at the instant that I start going, that way, at that instant, while I'm still at that purple point, r would momentarily be constant. And that's that vector. So these are what you call your polar standard basis vectors. And in various circumstances, they can be useful. Again, I'm not going to be doing anything with them in Math219, though. So I want you all to know what these things are. I want you to understand what we mean by polar standard basis vectors. You know, about coordinates increasing, the others being constant. And I want you to know that these formulas are there, right? I don't feel like you need to memorize these formulas. But it also, I want you all to entertain yourselves by deriving where these formulas come from. It's a healthy exercise. Likewise for cylindrical, likewise for spherical, and y'all can think those through. I'm going to wave my hands very quickly at a few things to be aware of. Notice, unlike in rectangular coordinates, they're not constants. Right? They are in rectangular, but they're not in, let's say, polar, for example, because at this point, for example, there's my standard basis vectors, but at this point here, right, my r standard basis vector is now like that. It's not the same. It depends on where you are. And so does the theta one. Right? So that's irritating. Well, the algebra doesn't work out very nicely. When you have rectangular standard basis vectors, you get this nice relationship. Coordinates become coefficients in a linear combination of standard basis vectors. One of our fundamental facts of linear algebra, right? Very convenient, very powerful, very useful fact of linear algebra there. Does not work in any other coordinate system. So, for example, in spherical here, it's just not. There's no relationship between the spherical coordinates of a point and how you would write that point with respect to its it just doesn't work in any sort of natural way like this that you would expect. So it's another sort of thing you have to let go of. But anyway, that's the main things I wanted to talk about. Just be aware that they exist, be aware of what they are, and we're going to call it a day right there. Y'all have a good rest of your Monday. See you on Wednesday.